What's up, everybody? Learning as a hobby here. I want to continue with uh, going through the appendices in Chapter 4 of Spivak. So I'm going to do the summary for Appendix 2 in this video. I haven't started on the exercise set for it yet, but that should come out either tomorrow or the day after, depending on how much time I have. And then on the weekend, I should be able to have time to get Appendix 3 done. And then we'll be done with Chapter 4 finally, and we can go on to something else. Not move on. I mean, move on to the next book in the cycle. So you know what I mean. Okay, so let me bring up the notes for Chapter 4 that I wrote up. Chapter 4 is on the Appendix 2 in Chapter 4 is on conic sections. So he starts by saying, most of what we'll do in this book is going to be in two-dimensional space, but this topic here, just briefly, we're going to go into three-dimensional space to look at conic sections, which are two-dimensional curves that you get by taking the intersection of planes with cones. So, we've seen three-dimensional space in some of the other videos that we've done already, but he starts with just describing, for three-dimensional space, we have the intersection of three perpendicular axes. One is called the x-axis, the other the y-axis, and the vertical one is called the z-axis. And you can denote any point in the three-dimensional space by three real numbers called the coordinates, right? So x, y, and z. It's just the analogous representation for geometric points for 2 dimensions, but just moved up 1 dimension. Okay, and then we go right into conic sections. So to get a cone, what you do is you take a line and you rotate it around the vertical axis. So the line has some slope C. So this, let me get the pen out here. So this line here has slope C, same thing here, right? So, all the sides of the cone have slope C, if you want to think about it that way. So we can find the equation of the cone by using the Pythagorean theorem. So for example, the slope C, whether it's positive or negative, is given by Z, which is the height that I have written here, divided by this distance here, which is x squared plus y squared square root, right? That's just the distance in the horizontal plane from the origin of the point x, y, 0. So using that formula, we get the general form of the equation of the plane. The negative version gives you sorry, not of the plane, of the cone. The negative part gives you the bottom cone, and the positive part gives you the top cone. All right, so XYZ is on that cone if and only if the Z coordinate is given by that function of X and Y. So plus minus C, square root X squared plus Y squared square root. Okay. Oh, and also I'm calling this equation 1 because we'll refer back to it later on. Okay, so what happens if we intersect this cone with some plane P? It's the whole point, right? Conic sections are given by the intersection of a cone with a plane. So, the curve might look something like I have drawn here. This would be an example of an ellipse or a circle, maybe. If you take the cross section, so in other words, cut this cone right down the center, right? So split it in half. Then you get this cross section here. The sides of the cone become these two lines. One of the lines has slope negative C, and the other has slope C. And the red line here is where the plane intersects the ZX axis. Sorry, the ZX plane rather. So in other words, the y-axis is actually coming straight out through the computer screen, or the TV screen, whatever you're watching this on, or your phone. So that the y-axis is sticking straight out of the perpendicular to whatever surface you're watching this on. Okay, so the line L here, for any point on the line L, has coordinates x, comma mx plus b, assuming that the line is not vertical. It has some slope m and some y-intercept b. But first, we're going to look at a simpler case where the line is vertical. So here, case one, if the plane is vertical so that the line L, any point on the line L has coordinates a, z for some constant a, then by the equation one, again, just to remind you what that is, that this is equation one over here. Plugging that in to that equation, we get z squared, after you square, z squared is c squared times a squared plus y squared, and you can solve for the constant on one side. So you get the equation c squared minus c squared y squared equals c squared a squared, which of course is the equation of an hyperbola. So this is the geometric picture here. So if the plane is vertical, it slices the cone like I have in the picture here, and the curve that is traced out in the intersecting plane is a hyperbola. You get two branches, right? So that's what you get in that case. And then case number two is where the plane is not vertical. So in other words, the line L has some slope m, right? So if XYZ is a point in the plane, then Z has to have the form mx plus b. Okay, that's if and only if, which again by equation one implies that mx plus b is plus or minus c times square root x squared plus y squared. Okay, so now what we want to do is we want to define coordinates in the plane P so that we can see what the shape of the curve is that's represented by the intersection of the cone and the plane. So what we do is, or what he does in the book, is he chooses L, the line L, to be one of the axes, and choose the other axis to be the line parallel to the y-axis. Remember, that's the one that's sticking straight out at us, passing through the point Q. The point Q is this point where the line intersects the x-axis, like I have drawn in the picture down here. All right, so what we do is on the axis L, if this distance from Q to this point, which I'm calling sort of like capital X, if this distance is capital X, we can write that distance as a function of the original X coordinate of our original X axis. Notice this is a linear projection, an orthogonal projection onto the X axis of the vector X. I don't know what to call that, capital X maybe. So that you get a linear function. X is a linear function of little x, right? So alpha and beta are some constants. And from that, whoops, meant to erase that. Right, so the points in the plane, and I should say also, since the y coordinate is parallel to the q, the line through q, the y coordinates end up being the same as the original y coordinates. So if capital X, capital Y is a point in the plane, then it can be written in terms of x and y coordinates like this. So the capital X is alpha x plus beta, and the capital Y is just equal to the y coordinate, the original y coordinate. Okay, and plugging that into the equation that we had a minute ago, this one here, you get m times alpha x plus beta in parentheses plus b equals plus or minus c times square root in parentheses alpha x plus beta squared plus y squared. That's all under the square root. And then when you just do the algebra and multiply everything out, you get something that looks like this. Right, you get something that looks like this. C squared y squared minus alpha squared times m squared minus c squared times x squared plus some constant times x plus some constant equals 0. He just says you get some constants here. If you multiply this out and do the algebra, these will be some combination of the coefficients here. I didn't feel like multiplying it out either, so I just copied the equation that he has here. But if you're really skeptical, you can multiply it out and see what they are. Okay, so that's what the equation looks like. Now here, the curve that you get depends on the sign of m squared minus c squared. All right, and there's three cases. So either m squared minus c squared is 0, which means that m is equal to plus or minus c, or in other words, the plane is parallel to the generating curve of the cone. And in that case, you get a parabola, right? So just like I have drawn in the picture, I didn't really draw it very well. That parabola should be contained in the cone. But you'll have to excuse my poor drawing ability. But hopefully you get the sense of what I'm talking about here. All right, so if m is the slope of the line L, excuse me, is parallel to the generating curve for the cone, then you get a parabola as the intersection. Right? Case number 2, if c squared is greater than m squared, which means, maybe I should say in case A, that means that this is 0, right? So you get something that looks like that, which is the equation of a parabola, right? Your quadratic term is y squared, and notice that you have a linear factor of x here. So you get a parabola. If this thing is positive, whoops, sorry. If this thing is negative, then you get a plus sign over here because negative times negative is positive, right? And that gives you the equation of an ellipse. So in case B, you obtain an ellipse. And again, you'll have to excuse my drawing here, but what that means is the plane slopes less than the generating line of the cone, which means that when you take the intersection, you get either an ellipse or you get a circle if the plane is horizontal, right? All right, that's case 2. And lastly, case C, if c squared is less than m squared, we obtain an hyperbola, meaning that the slope of the line L is greater than the slope of the the slope of the generating line. So in other words, that means that this thing here, the sign of this is positive, so this stays negative, and that gives you the equation of an hyperbola. All right, so that's what I'm saying here, and you can see the picture of why that happens. So if c squared is less than m squared, we obtain a hyperbola. The plane slope, in other words, the plane slopes more than the generating line of the curve, and this is the picture behind it. All right, so those are the 3 cases. That's essentially Appendix 2. It's relatively short, and there aren't that many problems in this appendix. I think there's 3 problems, but some of them have multiple parts. I haven't had a chance to start on those yet. Let me just stop the screen share so I can end this video. I'm going to try and start working on the problems tonight, but I probably won't have time to finish them tonight, and I'm not going to have a whole lot of time tomorrow. But I'll work on them, and who knows? Maybe I'll finish it before Friday night. Maybe I can post a video for the exercises tomorrow, and then I'll have the whole weekend to do Appendix 3. So let me know what you guys think down below, and I'll see you in the next video, which should be coming out either tomorrow or the next day. And I'll also have Appendix 3 coming out over the weekend for Spivak. All right, guys, so until that time, keep learning, and I'll see you in the next one.